Hello and welcome to Answer Everywhere. This is a live show where every week we take a look at a unfamiliar code base and poke around and try to do some code archaeology to sort of see what makes the thing work. This is the fourth rendition of Fan Request Roulette, where I take a bunch of the fan requests that I've gotten and choose one at random. You can see here is the list of projects that people have suggested. So lots of great stuff, including, for example, Grub, Xterm, Wayland, GNOME, KDE, Q emulator, all sorts of wonderful stuff. So we're going to do our normal process where we take as our source of entropy the latest Bitcoin price, which I have here, and the latest Taylor Swift tweet, which I have here, and we'll just run them and generate a seed. All right, and here's our seed list. And I'll grab these and I'll use them to sort the spreadsheet columns. Let's see if I can just paste these. All right. Let's sort by weight. All right, cool. So we're going to take the top, what is it, 20, I think. So down here, we'll get rid of these empty lines. And we see a couple of multiple requests from some users. We'll make sure that only one user has, that each user has only one request per episode that's being considered. I think that's good. These are all different people. I think, unless they're secretly the same person. Can I delete these simultaneously? No? Okay, well. All these empty lines. It's because I had my my list that I pasted in was too long. That's okay. Try to remember that next time. All right, and let's get rid of these multi requests here. And so here are the top 20, I think. All right, and so we'll roll a d20. Do I even understand what I am doing? I rarely understand what I'm doing. Pop out chat. Here we go. The Spud, that's what we're deciding. And Naeem Khan, yes, also that's what I'm deciding. So I'm thank you, John. I'm picking one randomly. And the way I'm picking one randomly is I'm just getting a source of entropy. And what was I going to do? First of all, this is not in the VM. And so now these are the top 20 candidates, and now we're going to roll a d20 to find which one is the true winner. All right, 14, which is actually 15 because one is consumed here. But just for fun, let's number these from 1 so nobody thinks that I'm fibbing. Whoa. Is that really how you completed that series? Numeric? What if I give you 4? All right, it's not going to do it. Anyway, this is 14. I have no idea what it is. lwIp. Let's figure it out. the code alchemist. All right. Actually, I think I do remember what this is. I think it's like a small IP implementation. Is this an I or an L? I think it's an I. Let's look at the Wikipedia page. And we're done with this spreadsheet. Wikipedia doesn't seem to know about it. Is it IWLP? What if I just try copying it? Yeah, this thing. Oh, lwIP. There's the first I that wasn't an I. Okay. Lightweight IP is a widely used open source TCP IP stack. Cool, designed for embedded systems. It was originally developed by Adam Dunkels at the Swedish Institute of Computer Science and is now developed and maintained by a worldwide network of developers. All right, it's used by many manufacturers of embedded devices, including Intel/Altera. Wait, are Altera and Intel the same thing? Analog devices, Xilinx, TI, ST, and Freescale. The focus of the lwIP network stack implementation is to reduce resource usage while still having a full TCP stack. This makes it suitable in embedded systems with tens of kilobytes of free RAM. Tens of kilobytes, that is small. And room for around 40 kilobytes of code ROM. Okay, it has several other important parts such as network interface, operating system emulation layer, buffers, and memory management section. Okay, so this looks like small TCP/IP. I'm going to look at Altera though. Founded in 1983 and acquired by Intel. I didn't know that. Okay, so I guess just for fun, let's ask, how does the lwIP TCP implementation differ from the Linux kernel implementation? So we have looked at a couple of things in the Linux kernel. We've looked at the TCP stack, and we've looked at the sockets, as well as there's an older video on just like poking around the kernel in general. All right, so we see modularity and footprint. It's designed to be lightweight, yeah. On the other hand, it's part of a comprehensive networking subsystem that provides various features and scalability. It's primarily designed to be run on bare metal, a simpler API. Okay, so let's find the code. Maybe Wikipedia will link to it. Here's the website, and I guess it's on Savannah. Okay, is it also on GitHub? See if it's on GitHub. These are mirrors, I guess. But what commit are they on? E2980. Sorry, E29870. And this is on something. Where's master? E29870. Okay. So this GitHub mirror seems to be good enough. I'll just assume that it is. And here's their webpage. I don't know if, I guess this is useful. Zero copy RX. Ethernet driver. All right, so let's look on GitHub and actually download their code. Somewhere I think I have a shell, maybe not. All right, Cool. And the other thing I guess we might as well do is have source graph. Just to have all the tools. Okay, so let's pop this out. So I don't really know what to expect here. My uncle has a PhD in embedded networking. Weirdest dude out there right now. that's kind of funny. I'm curious, Zohaib, what era was your uncle working in embedded networking? And all of a sudden, there's cloud cover. So at least on my preview here, my screen is very dark. Is this how I look in real life? I guess that's okay. Let me see if I can fix this a little bit. Yeah. Whatever. Okay. All right. So I'm not sure what to expect here. I don't know how lightweight is, but it could be small. We've got API, apps, core, include, and netif. So that's not much. Let's at least, I'll look at these directories, and if it's really small, I might just open this in Emacs. And it does look to be really small. But we got folders here, apps. But do we care about apps? I'm not sure we do. Like HTTP? No one cares about HTTP anymore. No, just kidding. I guess maybe we'll ignore apps for now and focus on possibly the API, and then we have include. I'm not sure what netif is. Okay, so all the header files are here. And whatever netif is. Post 2010, he made significant contributions. He is very proud of that. Oh, cool. That's awesome. Well, I'm glad he's doing cool stuff. Netif, maybe interface, network interface. We see bridge here, Ethernet. I'm going to guess netif is interface. So since there's not so many source files here, I don't have to rely on browser tabs to keep a queue for me. I think I can just go into Emacs and take a look at things. All right. So I guess let's start in where should we start? Maybe in the headers. We have lots of headers, but relatively few things in the API, which are C files. So I'm wondering if maybe there's actually lots of implementation in the headers. Let's take a quick look at the API stuff. We have API lib and message, netbuff, oops, and TCP IP, sockets. I'll ignore netDB and the other stuff. All right, so let's open up. How about API message? Yeah, Adam Dunkels. Is he really like the sole author of this? Okay, so what do we have? About 2,000 lines. That's a lot. And we're including some stuff from, I guess, the include directory, including ip.h, UDP, TCP, and raw, kind of as you would expect. And what are we doing? We've got this lwIp netcon error to message. Translate an error to a unique void passed via an mbox. Mbox is maybe message box. lwIp netcon is error message. And then lots of, I'm just jumping to the bottom for fun. And we've got this style here where the return type is a line above the function, which makes it a little bit harder to list all the functions with a regular expression. But maybe source graph will do it. I don't know. Where my message? Can I get a list of, I can get symbols. It's not bad. Are these symbols in here, like error TCP? Okay, so these seem to be functions. Let's just scroll through the functions and see, just get a feeling for what's here. Net connection, do DNS, do get host name, receive, drain, free, poll TCP, receive raw, write delayed param. Okay, let's look at poll TCP. Oop, let's spell it correctly. The poll callback function for TCP netcons. I'm guessing netcon is a network connection. Wakes up an application thread that waits for a connection to close or data to be sent. We're going to wake up an application thread. And that thread is going to wait for a connection to close or data to be sent. The application thread then takes the appropriate action to go on. And it signals connection sem .net close. What? Net. I guess maybe this is one line and then this is a separate thought. Netcon close waits for consem if closing failed. All right. So poll TCP is going to take some args, avoid star, which I guess means you can pass it whatever you want, and then a TCP PCB pointer. Do I have no? So the code alchemist. This is a good question. I don't have different key bindings for Firefox. I just use regular key bindings. But one of the reasons that I use the browser for code is I don't have a great way to do. I think the tab interface in browsers is a little bit better than the source code interface for pulling up like a queue of things that you want to process in order. You can do that sometimes in code editors, but I just find it more convenient on the browser. Okay, so just to get a sense of what these concepts are. So everything has a maximally contracted name. So you kind of have to reverse engineer what they're thinking of in order to read the code. I'm not really sure if short names actually make an efficiency difference in embedded code or in general. Let me ask. So ChatGPT is telling me that the length of variable and function names don't have a significant impact on the resulting binary. The compiler translates the source code into machine code instructions. Yeah, that's what I thought. The resulting binary contains these instructions. Information such as symbols. The length of the is typically discarded during the compilation process as they're replaced for memory addresses of offsets. However, there are a few cases. The symbol table size contains information. Yeah. If you have a large number of symbols with long names, the symbol table can increase in size, which may marginally affect the overall binary size. And then debugging information. Yeah, well, this makes sense. I never know whether people who write code with this kind of like telegraphic style, if this is if this is optimizing for a known important thing, or if this is just like the style people like to use. All right, anyway, so we're going to check the connection state, and if it's netcon write, so I guess it's ready to be written, or it's in the writing state, we're going to call do write more, and pass in con and con write delayed. But what are we writing? Also for a netcon close, we've got this if thing. If lwIp so send timeo, maybe timeout, and then linger, and we'll check some stuff. And decrement polls left. So I guess we're keeping track of how many polls we have. And then we'll do close internal write delayed. And then we'll check if a non-blocking write failed before. Then check available write space. If connection flags, and then we're going to end the flags with netcon flag check write space. So I guess that's how you check the write space. And if that succeeds, I suppose we interpret that to mean non-blocking write failed before. And if our counts for queued bytes or pbuff count drops below the configured low water limit, let select mark this PCB as writable again. So if we don't have too many queued bytes, I guess, and I'm not really sure what pbuffs are, some kind of buffer. I don't think they're protocol buffers. Then I guess we can send plus. Let's look at send plus. Does that mean you can send more stuff? Where is tags? I think tags is just here. Here are the netcon events. We can receive plus, receive minus, send plus, send minus, or error. So this is like, we're sending these as signals, I guess, to say that we can handle or not handle more stuff. Used to inform the callback function about changes. Event explanation. In the netcon implementation, there are 3 ways to block a client. Accept an mbox using sysarch mbox fetch con accept mbox accept pointer in netcon accept. We can receive an mbox, and we can send queue is full. These events have to be seen as events signaling the state of these mboxes or semaphores. For non-blocking connections, you need to know in advance whether a call to a netcon function call would block or not, and these events tell you about that. Receive plus events say, safe to perform a potentially blocking call once more. They are counted in sockets. 3 receive plus events for accept mbox means you are safe to call netcon accept 3 times without being blocked. Same thing for receive mbox. Okay. So you get some sort of quota. And this is, the quota is like managed with these receive plus and receive minus events. And if you have a quota of 3, then you can call netcon accept 3 times before you're blocked. I'm not sure exactly what netcon accept does. It accepts something. And I still don't know what an mbox is. And receive minus says, your call to a possibly blocking function is acknowledged. Socket implementation decrements the counter. Your recall to a possibly blocking function. Okay, so when you're ready to call a function that might block, I guess you emit receive minus. So maybe that's not managing your quota. Maybe that's just, maybe that's not somebody else managing your quota in the sense of like rate limiting you. Maybe it's more like you're sending out a notice that you're going to spend one of your units. And for transmit, there's no need to count. It's merely a flag. Send plus means you may send something. Send plus occurs when enough data was delivered to peer, so netcon send can be called again. A send minus event occurs when the next call to a netcon send would be blocking. Okay, and what else can we do? We can netcon join and leave. Where are we? API.h. We've got some netcon DNS stuff. Or declare some structs to avoid to include their headers. And so it's just a bunch of PCB stuff, mostly, and a callback. And here's a netcon. It's a struct. Let's see. We have a type, which is either TCP, UDP, or raw. So it's a kind of connection. And okay, so this is basically the type of, maybe like the type of socket. And then we have the current state of the netcon, which is some state. Is this the same as what was up here? That's a netcon event. I don't know what netcon state is yet, but we'll find it. And then we've got an lwIP internal protocol control block, which has some stuff. Okay, so PCB is protocol control block. And we have different ones depending on whether we are IP, TCP, UDP, or raw. Then we have some error stuff like a pending error. And in mbox, where received packets are stored until they are fetched by the netcon application thread, which is a sys-mbox type. And then what is this thing? We have a callback arg, which is a union, I guess, of a pointer and a socket. And some timeout stuff and buffer size and whether to linger. Okay, and a callback. What is a netcon? What was it? State? I think we might have seen this. Okay, so none, write, listen, connect, close. All right, non-TCP netcons are always in state, netcon none. All right, so this is really only for TCP, which makes sense because TCP is connection oriented. And the netcon types are these: TCP, invalid, UDP, UDP lite. I'm not sure what UDP lite is. IPv6, raw, etc. Cool. I still don't know what an mbox is. I have a feeling this is something larger than just this repo. Let's see if Wikipedia knows about mboxes. The generic term for a family of related file formats used for holding collections of emails. That's not what this is, though. I don't think. All right. It seems like most of the stuff wants to tell me about, was it sys, about mailboxes, sys-mbox t. We'll type def the struct sys-mbox t. Okay, sorry. Wait. Whoop. Sys-mbox t, I guess, is the same as sys-mbox. And sys-mbox is just a void star called mbx. And so what does that mean? It means it's basically an arbitrary pointer to memory. So I think it's essentially like a box, a memory box, like a maybe like a Haskell mvar, like a mutable thing that you can put stuff in. I'm not sure if that's the right way to think about that. If you know the right way to think about this, let me know. Otherwise, I guess I'll ask Bard. Let's ask Bard. That's a good question. So the bangs are DuckDuckGo. Yeah, it routes it to a different search engine. So I can bang W is Wikipedia, bang G is Google, nothing is DuckDuckGo or dictionary. Oops, I spelled incorrectly. Just a bunch of different stuff. It's just a nicer kind of universal interface to searching. So an inbox is a mailbox, which is a data structure that allows multiple threads to communicate with each other. Okay, a mailbox. I guess that is what M stands for. That yeah, I get mail and message. They're not too far apart, I guess, but not in the sense of like a mail user agent or whatever they're called. Email. It's not in the email sense, I don't think. The mbox of the struct is a pointer to the actual mailbox data structure. It's used to check if the mailbox is valid, and then is used to check if a pointer in the mailbox is valid. To think about what an mbox is, you can imagine the post office. Yes, an inbox is basically just a region of memory that is used to store messages. The messages in an inbox are stored in a queue, and threads can post messages to the queue and fetch messages from the queue. If it tries to fetch a message from an empty queue, it will block until a message is posted. Well, how do you know that? Post a message, fetch a message. How do you know that it blocks? Is this a general thing? Mbox data structure. Oops. You can see I made typo. Email format. What if I just do negative email? What is going on? This is wild. Okay. So this has message receive, and then we've got some semaphores. I guess this is just a common... the mailbox is not a Solaris feature. To use it, you need all files provided on this page. Okay. So I think it's just a common idiom. So I'm just going to verify this, that it's not like a operating system feature. It's a relatively obscure data structure that's not used very often. Useful in certain situations, for example, to implement a producer-consumer pattern. And you could also use queues and stacks. Yeah, that's what, if you're not familiar with Mbox, you can safely ignore it. Thank you. I'll say, tell me about the security implications of using a void star as a... I'm just not sure. I mean, usually you don't see people these days like passing around void stars and like sending messages into them. I guess it is guarded by a mutex, which is an important sanity thing. Anyway, where were we? Okay, so accept mbox, I guess, means we're going to accept a message from the mbox rather than accept the mbox itself. Mbox where new connections are stored. Okay, this is the mbox where you accept stuff. So we have API message. Okay. So this is all API message. That's fine. I don't need to, I guess, dig too much in API message. I just kind of wanted to see what that was about. Let's look at TCP IP. No sys, don't build if not configured to use lwIp. Okay, and then what are we including? We've got the TCP IP prive.h and a bunch of memory stuff, NIP, and a pbuff, and some ETH stuff. ETH ARP, I guess the ARP protocol maybe an Ethernet. TCP IP message var ref. I don't know if var declare, alloc, and free. I'm not sure what these are doing. We've got some global variables, like whether TCP init is done. So Code Alchemist is asking mbox like some event carrying bus or something. I guess I think it's more primitive than that. It's like just it's just a pointer to some piece of memory. So you can put messages in the memory and like tell people to like, look in memory location 4 and take everything that's in it. But it is used to pass messages. Like if you imagine like a regular mailbox, you can put something in it and take it out, that sort of thing. It can allow for arbitrary code execution. This is because the void star can be used to store any type of data, including pointers to functions. If an attacker can control the data that is stored in the void star, they can then use that data to execute arbitrary code. Sir, to execute this vulnerability, An attacker would first need to find a way to inject their own data into the void star. This could be done by exploiting a buffer overflow vulnerability in the code that uses the void star. Once the attacker has injected their own data into the void star, so I apologize. Everyone in my household is now newly sick, so I have to pause every so often. So to exploit this, this can be done by exploiting a buffer overflow vulnerability in the code that uses the void star. Once the attacker has injected their own data, they can use that data to execute arbitrary code. Yeah. To mitigate, you should avoid using void star as a mailbox. Instead, you should use a data type that is specifically designed for storing messages, such as a struct or a union. You should also make sure that the code that uses the mailbox is properly protected against buffer overflow vulnerabilities. So here are some example tips. Use a struct or union. Make sure that the code of the mailbox is properly protected against buffer overflow. Use a secure coding style, such as MISRA C coding standard. Use a static analysis tool and get your code reviewed by a security expert. Those are all good ideas. Okay, so back to the TCP IP implementation. We've got mbox fetch, which will wait for a message with timers disabled. For example, pass a timer check trigger to the TCP IP thread. Yeah. And here's another TCP mbox fetch. And which one you get depends on whether you've defined lwIp timers. This function here waits, I guess, forever for a message to arrive in an mbox while waiting timeouts are processed. So I guess, so we're doing embedded, right? So we have a small amount of memory. And I guess the way that they're dealing with having a small amount of memory is they're just using some region of memory and they're shoving all messages in there. And what I don't know yet is whether, I guess, if you have different connections open, they probably have their own regions of memory, although I'm not sure. Maybe you just multiplex over the same region of memory. I guess we'll find that out. Okay, and we've got some sleep time. What is this? Okay, mbox fetch. We're going to make sleep time. We've got this again, which I guess means we're using a goto. And then we'll assert that the core is locked, whatever the core is. Can we find out what the core is? Following defines must be done. This check core locking. What is core? Sys arch. Embedded systems should check that we are not in an interrupted context here, e.g. core, cortex, M3, M4 ports. Instead, we use a more generic FreeTOS functions here. So maybe core is something embedded related, which I will black box for now. But here's the again label. And we'll get the sleep time, and we'll check if it's equal to this to infinite sleep time. And if it is, we're going to unlock the core. Well, specifically the TCP IP core. And then we'll call mbox fetch and then relock the core, and then we'll return. Otherwise, if sleep time is 0, we'll call sys check timeouts. We try again to fetch a message from the inbox, and then we'll go to again. I don't know why this isn't just a loop, but why are we checking if the sleep time is infinite? And we're not checking if we have no sleep time. So it seems like sleep time is the opposite of it's not the time you're supposed to sleep. It's something like the opposite of that. At any rate, if we get down here, we're going to unlock the core, and we'll call mbox fetch with the sleep time. And if we get a result, I guess this probably blocks according to the sleep time. And if we get a result, we'll lock the core. And then we'll check the sysarch timeout. And if a value is returned, a timeout occurred before a message could be fetched. So we timed out. And then we'll check syscheck timeouts. We'll call syscheck timeouts that is, and then we'll try again to fetch a message. Okay, so what does syscheck timeouts do? Handle timeouts for no sys equals 1. Use sysnow to call timeout handler functions when timeouts expire. Must be called periodically from your main loop. Okay, so everything's going to check timeouts. And we'll assert that the core is locked. We'll get the time now. And we've got this do thing. Time less than next timeout. I'm just kind of curious, where is the actual timeout thingy? Calling next timeout, which is not passed in. What is next timeout? This sys_timeo thing. This timeout got a time and a handler, and it's just a struct that has timeouts. I guess it's like a linked list of timeouts, right? So we've got a pointer to the next one, which is the same type as we are. It's recursively defined. And we've got some handler that I guess we can call. Okay, so that's basically what a timeout is. And we're going to check them periodically. And here's the main lwIp thread. This thread has exclusive access to the lwIp core functions, unless access to them is not locked. Other threads communicate with this thread using message boxes. It also starts all the timers to make sure they are running in the right thread context. Okay. So this might be what is meant by the core. So this is like the main thread. Maybe if you've done like UI programming, the UI thread is like the main thread, and then you want to try to keep that thread lean. And anything like a user input, you're going to have some other thread handle it. And I'm guessing we're going to see a somewhat similar pattern here. So let's see what we got. So TCP IP thread is what the thing is called. And you know what? I should be... I should be changing the name of this stream so that people know what's going on. So let me do that for a moment. Okay. So here's the TCP IP thread. And we've got the struct message, an unused arg. I'm not sure why. We're going to mark the thread, I guess. And we're going to lock the core. And we'll check whether TCP initialization is done. And if it's not null, we're going to call TCP init done with whatever TCP init done arg is. And if it is null, I guess we just ignore it. And then while one, so forever, we're going to call this thread alive function. I guess maybe that's like a heartbeat, so that if you don't receive thread alive, you know that something has died, perhaps. Let's actually look at that. Determine this is something that triggers, define this to something that triggers a watchdog. This is called from TCP IP thread after processing a message. Yeah, I guess watchdog is the same thing. And then we're going to call, okay, wait for a message. Timeouts are processed while waiting. And then we're going to call mbox fetch with the TCP IP mbox. So this is the core. So I guess we have just one mbox for TCP IP. And maybe all the connections use the same mbox, perhaps. And at any rate, it says we're going to process the timeouts while waiting. And so if we peek at this function, which I think we'll do in a minute, we should see it calling the timeout processing function. And then if we're done here, if TCP mailbox fetch returns, then I guess we've got some sort of message. If that message is null, then we'll emit some debug stuff saying that we have an invalid message, and we'll assert that we got an invalid message, and then we'll continue. Otherwise, we have a valid message, and we'll call TCP thread handle message, TCP IP thread handle message, which I guess is handled on the same thread. So let's look at mailbox fetch real quick. It's just you're not going to show me the definition here. Sys.h. Note that a function with a similar name, sys mailbox fetch, is implemented by lwIp. This is okay. At any rate, it says it's going to wait for a message with timers disabled. We saw this function before. Okay, whatever. So here, let's take a look at handle message. So handle message is going to handle a single TCP IP message. This is in its own function for access by tests only. Yeah, okay, so we can test it. That's good. All right. We're going to switch on the message type. Yeah. And here, what are the types? We have message API call, callback, static wait, locking input. What? Let's take a look at this enum. This should be just an enum, right? I think it's trying to find all instances of the word type. That's not what I want. Is there a message here? This is probably it, right? So we've got an enum of TCP message type here, which is, yeah, so we've got this API call in packet, I guess. Timeout, untimeout, callback static wait. And then a TCP IP message has the type and a union of a bunch of stuff, including, so an API message is a message, which is a void star again. So just some region of memory essentially, and a callback function. And then an API call, I guess, is maybe a semaphore, and a TCP IP call data structure thing in a function. Then a call, and then a CB wait is a semaphore or context in a function. I guess CB wait is a callback wait. In is an input with a maybe network interface and a protocol control block or something, whatever pbuff is. And a callback is a function with a context. TMO is probably timeout, has args, a handler, and some time. Okay, so these are different kinds of messages. These are not like standard TCP messages. I guess these are messages in the context of this particular software. So I don't know, an API call, I guess we're trying to call the LWIP API. And we're passing in, why are we passing in a semaphore? I guess we have to lock something, maybe lock the API. And we've got some function that we're calling some function, some API function, and these are presumably just the arguments to the function. So we're like remote procedure calling, I guess, ourselves essentially. is how I'm going to think about that. And so handle message is just going to call different, it's just going to dispatch the thing that we pulled out of the mbox and pass it to different functions. It seems like. And these are just hard to read, so I'm not sure. But let's pick one, I guess. How about in packet? And we're going to have this debug thing. I guess maybe that only runs if there's debug systems symbols enabled. Then we have this if message imp if message right arrow message.imp input underscore fn, and we're going to call that on message arrow message.imp and message to message.imp.netif is not arrow okay. Then we're going to call pbuff free. So we're going to free, I guess, whatever the p is. And then we're going to call memp free on the in packet from the message. And then we're going to break. So whatever this stuff is, so the message has some input. And it's got some input function. And then I don't really know what p is. And I'm guessing netinf is the network interface. Let's look at netinf. So netinf is a generic data structure used for all lwIp network interfaces. The following fields should be filled in by the initialization function for the device driver. Hardware, address length, hardware address, MTU, and flags. Cool. All right. And what else do we have? Okay, so let's get rid of net. Got this IP6 route entry. All right, so what I don't know next is, so we're going to route this somewhere. So let's take a look at, see if we can do like life of a packet. So input packet. Pass or receive packet to TCP IP thread for input processing. So I still don't know what pbuff is. Let's see what pbuff is. Maybe packet buffer. That would make sense. So SNMP pbuff stream. We've got struct pbuff. Main packet buffer struct. Here we go. So packet buff has a next, which is also a packet buff. Singly linked pbuff chain. Then pointed to the actual data in the buffer, which is a void star again. Then total length of the buffer, the length, total length of this buffer, and all next buffers in chain belonging to the same packet. Okay, so we know somehow what all the, everything that belongs to the same packet. This is the length, and then just the length of this particular buffer, which is one link in the singly linked list. And we have type internal, which is a bit field indicating pbuff type allocation sources, and some flags. And then we've got a reference count equals the number of pointers that refer to this pbuff. This can be pointers from an application, the stack itself, or pbuff next pointers from a chain. And then for incoming packets, we've got the network interfaces index. So I guess we've got some list of network interfaces. Which is actually kind of interesting because is it possible the network interfaces get out of order? If we don't refer to network interfaces by some more stable identifier, I'm wondering if that's a way of messing around with putting something in the mbox. Then in case the user needs to store data, custom data on a pbuff, we've got some custom data thing. Okay, so pbof is packet. That's good. So TCP IP input packet. We've got we're going to give it a packet buffer thingy. Yeah. And we're going to give it a network interface. And we're going to get it a network interface input function. And input function to call. And so each network interface, I guess, defines its own function that's going to decide how it wants to handle incoming packets. Is that the idea? Function prototype for netif input functions. This function is saved as input callback function in the netif structure. Call it when a packet has been received. Okay, so that's how your application decides that's how I guess lwIP decides what to do when it gets a packet, right? And that's basically all it needs to do at this point, I think. So we've got this debug stuff. We're going to lock the core. We're going to call the input function and get the return value. Then we're going to unlock the core. Then we're going to return the return value if we have locking input set. Otherwise, if we don't have locking input set, we'll do some other stuff, which I'm going to ignore. And then here's whatever TCP IP input. Pass a received packet to TCP IP thread for input processing with Ethernet input or IP input. Don't call directly, pass to netif add. How is this different, TCP IP input versus TCP in packet? Pass a received packet to TCP IP thread for processing. Pass a received packet for input processing with Ethernet or IP. I guess this is for just different protocols. Yeah, I guess this is for the Ethernet protocol or the IP protocol instead of TCP. Okay. Try callback. Call a specific function in the thread context of the TCP IP thread for easy access synchronization. Okay, so I think I have a pretty good idea about what this stack is doing for TCP IP. We've got this mailbox thing, and there's a main thread that's going to just look in the mailbox repeatedly. And when it sees something that matches a network interface, it's going to call a callback that's sort of indexed by what network interface that is. And so if you're an embedded device, you might just have one network interface, or maybe you have like a wireless interface and a wired interface. And so maybe you have different functions that handle things like that. Is there anything else we want to see? I guess let's look at sockets. BSD-like API module. Lots of defines. Lots of things like address to port. Just different like computations. What is sign 6? IP address port to sock address. It takes SN6. Maybe something input 6. Socket input 6 and IP address and port. And we're just going to do some computations on them. A struct sock adder replacement that has the same alignment as sock adder in instantiated. So I'm just going to quickly look through socket to see if there's anything that really stands out as being like an interesting algorithm or an interesting structure. Thread cleanup, sock inc used, thread safe increment of sock FD used with overflow check. Okay. We're just going to, it looks kind of like reference counting stuff. Done socket in full duplex mode. Sock FD used not equal to 0 prevents a socket descriptor from being released and possibly reused. When used from more than one thread, for example, read while write or close while write, etc. This function is called at the end of the functions using try get socket. Cool. All right. So, but where's the actual protocol stuff? Unmark this stuff. What is API lib? All the lower part of the netcon function. This function is then running in the thread context of TCP/IP thread and has exclusive access to lwIP core. So this function has exclusive access to the core code, which is API message. Netcon API message. It's going to take a callback function and an API message and return an error. And what are we going to do? Well, I'll ignore the debug stuff. I'll ignore this sem per thread, I guess. And I'm just going to call TCP/IP send message wait sem with the function, the API message, and return an error. What does this function do? Sends a message to TCP/IP thread to call a function. So we're going to ask the TCP/IP thread to call a function. We're not going to call it directly, I guess. Caller thread blocks on a provided semaphore, which is not automatically signaled by a TCP/IP thread. This has to be done by the user. It is recommended to use lwIP TCP/IP core locking, since this is the way with least runtime overhead. Okay. You're going to give it a function to be called, the API message argument to the API function, the semaphore to wait on, and whether in some error. Send message await semaphore. So we're going to say that the semaphore is unused, I guess. Then we're going to lock the core. We're going to call the function on the API message, and then we're going to unlock the core. Then we're going to return error OK. Do we ever return anything that's not error OK? Maybe some of these return something other than error OK. Like, let's try. That's not going to return anything. Lock. Doesn't seem like it returns anything. The function. Do void. What else can return? Another error if not. I don't know how we get other error types. Unlock. I'm not sure. Maybe one of these can return it. Okay, and then synchronously call function TCP/IP thread. Yeah, but where's the TCP/IP like? There should be essentially some state machine. There should be some flow control. Do we get that here? Maybe in apps? Well, we have HTTP. We have LWI perf. And something about TLS, alt CP TLS, we have MDNS. I don't think it's an app, maybe in core. Yeah, maybe init, IP, DNS, def, pbuff, raw, stats. How about TCP? Common functions for the TCP implementation, such as functions for manipulating the data structures and the TCP timer functions. Yeah. TCP functions related to input and output are found in TCP in.c and TCP out.c, respectively. Here's the connection setup. The function used for setting up connections is similar to that used in the sequential API of the BSD socket layer. The sequential API. Okay, a new TCP connection identifier, that is a protocol control block, PCP, is created with the TCP new function. This PCP then can be either set to listen for new incoming connections or be explicitly connected to another host. So we get TCP new, bind, listen, accept. Yeah, connect. And for sending, we have write, output, sent. It's sent by enqueuing the data with a call to TCP write and triggering the send by calling TCP output. I'm wondering how they queue it. Maybe they just use a linked list again. Receiving TCP data, similar. And then polling. When a connection is idle, that is, no data is either transmitted or received, lwIP will repeatedly poll the application by calling a specified callback function. This can be used either as a watchdog timer for killing connections that have stayed idle for too long or as a method of waiting for memory to become available. For instance, if a call to TCP write has failed because memory wasn't available, the application may use the polling functionality to call TCP write again when the connection has been idle for a while. Okay, so so that's polling. Okay, so this is the TCP implementation stuff. And how long are we? Well, 26,000, 27,000 lines. Extra arg set. Let's see. Let's just reduce our font size here and see if just to get a feel for if there's anything that looks like it's interesting in implementation. TCP closed. TCP abandoned. Looks like it's got a big implementation. TCP raw. Let's look at TCP raw maybe. Some TCP timer. What is this? Slow timer. Queue. TX now. How many segments are freed? Kill state. Okay. Well. Let's also take a look at the TCP in. This is also about 2,000 lines. And what do we have here? Sequential API for thread model. And here we get the, wait, no. Not what I meant to do. We're in the wrong place. Let's go back to core. In is what I wanted, right? So we also get some big functions here. TCP input, the initial input processing of TCP. It verifies the TCP header, demultiplexes the segment between PCBs, and passes it on to TCP process, which implements the TCP finite state machine, followed by the IP layer in IP input. Cool. So I guess let's trace an input packet, shall we? Let's do it. So TCP input, we've got this PCB stuff and a PCB listen. PCB and previous are both TCP PCBs. And we might reuse stuff, I guess. And we've got header length. This unused arg thing, what is it doing? Eliminates the compiler warning about unused arguments. Okay. Assert, and then we're going to, I guess, assert that the core is locked. Whatever perf start is, maybe start performance metrics. And we're going to do stats. We're going to get the header from the payload by casting it as a struct, a TCP header struct type. And we'll check that the header fits in payload. We'll look at the payload length and check that it's smaller than the header length. And we'll drop short packets. And we'll go to dropped. I guess dropped is some sort of air condition. And then we're not even going to process incoming broadcasts or multicasts. So I guess maybe one of the ways it gets to be small is that it's going to just not support multicast or broadcast and drop those packets. It looks like checksumming is optional, which is a little bit surprising. I don't know what this pseudo thing is. Why is it pseudo? Calculates the IPv4 or IPv6 pseudo internet checksum used by TCP and UDP for a pbuff chain. I don't know if it's a pseudo checksum because that's how it's defined, or if it's doing some sort of cheaper version of a checksum. And we'll sanity check the length header. Yeah. Move the payload pointer in the pbuff so that it points to the TCP data instead of the TCP header. Okay, so we're just going to say that I guess we're done with the header. Then we'll look at the length and compared to the header, etc. And all options are in the first pbuff. Else, the TCP header fits into first pbuff. Options don't. Data is in the next pbuff. So we might have to look in more places, I guess, look further down in the payload. And we're going to trying to get the options. And I guess we're down here, we have options. So we'll convert fields in TCP header to host byte order. Okay. So we'll possibly change the byte order. And then we will get some flags. And the flags might be things like TCP fin and TCP syn. And if they are, we're going to increment TCP length. I guess, length. And if it's smaller than P total length, and then there might be an overflow, and we'll drop some stuff. And then if we're done here, we're going to demultiplex an incoming segment. First, we check if it is destined for an inactive connection. Okay. So if it's destined for an inactive connection, presumably we're going to drop it, right? If it's bound to... I guess we're just doing this by asserts. And then if we're down here, then we'll check the remote port. So if the PCB remote port is equal to the TCP header source and PCB local port is equal to the TCP header destination and some other stuff, remote IP address is I guess, equal to the current source address, and local IP of the PCB is equal to the IP current dest address, then we'll move this PCB to the front of the list so that subsequent lookups will be faster. We exploit locality and TCP segment arrivals. Okay. Not sure why we're checking all that stuff, but that's fine. And if PCB is null, and we're down here, then if we did not go to an active connection, we check the connections in the time wait state. Right? Doing more port checking. This is presumably for some sort of like routing. And then if we're down here, we're going to return. Finally, we still did not get a match. We check all PCBs that are listening for incoming connections. Oh, wait. No, this is... So IP current is our IP address, right? So I guess we're just checking if remote port is this source. I don't know what this check, why we're doing this check. TCP remote port. I don't know what it means for that to be different from the source and the header. But remote IP is equal to IP current source address. So if the TCP, if the packet thinks that we are the remote IP is what it's saying, and what it thinks is their local IP, I guess, is what we think is our destination. So that means that it's part of the connection. I think that's really what it's checking. And then we'll move packets around and increment and do some stuff with active PCBs. So we don't seem to be doing much else other than that. But if PCB is null, it did not go to an active connection. Maybe setting it to TCP active PCBs is the thing that sends it somewhere. Not sure. Doesn't seem like, I'm not sure really where it seems like if we match something, we should send it somewhere. List of all TCP PCBs that are in a state in which they accept or send data. Okay, so we're marking it as like in some state that says we accept it or whatever. But if it's null, we haven't matched anything. and they check the connections in the time wait state. So I guess we look at things that are waiting and less active, I suppose. And we do more checking of the IPs. And if we're done here, Oh no. Sorry. I must have turned off my mic. Um, how long will you not able to hear for? That's unfortunate. Hopefully you can hear me now, right? I must have accidentally left my mic off. Okay. Yeah, I'm so sorry about that. So what I was saying, hi, Evan. Hi, everyone. First of all, I'm getting bad data from YouTube. Okay. Yeah, so I'm sorry about that. Here's what I was trying to say. I was looking at the TCP input thing, and whoa now. Hey everybody. So yeah, thank you for checking. That could have gone on for a while, I think. Um, so the code is all pretty understandable in one sense. In another sense, it's a little bit hard to read. And so the sense in which it's understandable is that if we go to this TCP state machine, which I think is called process TCP or something, process something or other, TCP process. This state machine is all just you'd be able to track it really closely if you looked up the TCP standard. And so all they're doing is it's like a bunch of if statements and checking different, is the state this and is our local state this or that. And this is all pretty understandable. The input function itself, I think it's just called input, which is TCP input, which is the entry point, is a little bit more difficult to read because there's go-tos. So they have these kind of long jumps. And there's lots of these if-def things. And the logic is just kind of everything is jumbled up a little bit. So what input really does is it does parsing and it checks some headers. And then ultimately it calls TCP process if it finds a match. But those things aren't really sectioned out into functions that you could test. And so I think a lot of maybe when my mic wasn't on, part of what I was trying to figure out is just like what's going on in the function, the input function. So I would say that this input function, locally, it's difficult to read, but in terms of overall structure, it's really clear. It's pretty clear what it's up to. At any rate, we're going to hand off the TCP process, and TCP process is going to do the state machine. And at some point, it must. It's mostly modifying the the PCB. And I don't know if it ever calls another function. In some states, TCP receive is called to receive data. Okay. And the segment argument will be freed by the caller, unless the received data pointer in the PCB is set. Okay, so we're going to do things like TCP receive. Let's look at TCP receive. If there was any data contained within this ACK, we'd better pass it on to the application as well. So TCP receive is called by TCP process. Yeah, we saw that. It checks that the given segment is an ACK for an outstanding data, and if so, frees the memory of the buffer data. Okay, so if we send some stuff and they ACK it, then we can get it out of our memory. Next, it places the segment on any of the receive queues, such as PCB received and PCB lwIp. If the segment is buffered, the pbuff is referenced by pbuffref so that it will not be freed until it has been removed from the buffer. If the incoming segment constitutes an ACK for a segment that was used for RTT estimation, the RTT is estimated here as well. Okay, so we might estimate round trip type. And I don't think we've seen these queues yet, receive and usec, but that's okay. So we'll see if it's an ACK, and I guess we're just going to do the freeing. We're going to update the window. And the TCP sequence is, I guess, less than the send window something L1. And we're going to pass it in the sequence number as well. And then we'll do all of this stuff, some big computation to compute the window. Then we'll set the send window to send window scale. What is scale? I guess it's just going to scale it somehow. We're going to take the window and left shift by PCB send scale. And I guess the scale is the thing that maybe implements backoff, like exponential backoff, like how maybe it gets incremented every time we're told to back off or whatever. And then we're going to keep track of the biggest window announced by the remote host to calculate the maximum segment size. So we'll take a look at the window max, check whether it's less than the send window. And if it is, then we're going to set PCP send window max to the send window. I guess we're going to increase it. This can only increase it, right? And then we're going to send, what is LW1? LW1 is sequence acknowledgement numbers of the last window update. And then, okay, so the sequence number and the acknowledgement number we're going to keep track of. And then we're going to say that we received a window update. Very cool. All right. And then that's the Windows stuff, I guess, for ACKs. And then what do we do down here? From Stevens TCP IP Illustrated, Volume 2, page 970. It's only a duplicate ACK if some stuff happens. So this is the Stevens book, I think, is the classic book on TCP IP. For whatever reason, Volume 2 seems to be vastly more popular. I don't remember what's in Volume 1, but this is just some algorithm that they're just lifting out of this textbook, as they should. And this seems to be just a straightforward translation of the algorithm. I'm not going to look too closely at it, just because I've been here for a while. And then if we're done here, are we done with ACKs? Yeah, it'd be nice if in the code to know, like, when am I done with a function? It's a little bit hard to kind of like look at it and see what's going on. Whoops. Where was I? Stevens. Let's see if we can find the matching parenthesis. Electric pair mode, is that what does it? I don't know how to use this. Oops. My usual Emacs, I have a way of jumping to the end parenthesis, but I don't have it set up here. So, okay, so this is doing more ACK stuff. At some point, it's presumably going to like actually process data into a buffer or whatever, or a queue. If we're done here, I guess we get a comment. Maybe that's useful. If we're done here, the incoming segment contains data. We must process it further unless the PCB has already received a FIN. So if we're done here, we're going to process data. The code basically does three things. If it contains data that is the next in-sequence data, it's passed to the application. This might involve trimming the first edge of the data. If the segment has data that is above the next sequence number expected, the segment is placed on the OOSEC must be out of order. This is done by finding the appropriate place in the OOSEC queue, which is ordered by sequence number, and trim the segment in both ends if needed. And an immediate ACK is sent to indicate that we received an out of order sequence segment. Finally, we check the first segment on the OOSEC queue. We check if the first segment in the out of order queue is now in sequence. Yeah, for example, if received next is bigger than or equal to out of sequence number. If received next is, if that's true, then we must trim the first edge, etc. Okay, so I guess let's look at the nice case where we hand it off to the application. Is that the first case? Contains data that is the next in sequence. We do some asserting. We compute some offsets. Have some while loop while the length is less than the offsets. We'll remove header, which cannot fail. And I don't know what this else block is doing. It might be a duplicate block. The sequence number must be within the window in order to be further processed. Where do we actually like call the I don't know. Here we've received in sequence data. Adjust OOSEC data if fin has been received. So we might adjust our out of sequence stuff if we received in sequence data, I guess. Yeah. So this is lots and lots of stuff. So it's a small implementation. I guess it's smaller than the Linux kernel stack. We're down here, we might ACK. Okay, so I want to see, I'm not going to be here too much longer. I want to see the queues though. So OOSEC was 1. PCB received. Or, that doesn't actually seem to be referenced in the function. What about queue? Both queues are empty. So we have unacked, unsent. I don't know. Let's look at the PCB definition again. We've got a send queue length, a send buffer. We have unsent queued segments, unacked things that have been sent. We have out of sequence queue, received out of sequence segments. We have refused data, data previously received but not yet taken up by upper layer. I don't know what causes something to be refused. That's send. What about received? Okay, received. Function to be called when we receive, but that's not a queue. We have bytes act, unsent, oversized. I'm not sure where the receive queue is. We have receiver variables, receive next, receive window available. It must be somewhere. Send queue, unsent. I'm not sure. Okay, so we saw some Windows stuff. We have a general idea of what happens when it receives. It had that 3-part thing. It's mainly going to, if you receive it, it's somehow going to hand it off to the application. I didn't quite see where that's going to happen, but it's somewhere. And then we're going to possibly check out of order arrivals, and we're going to handle ACKs and all that sort of stuff. So we're at least getting a sense of an overall sense of how things are laid out, and we can trace the execution if we're motivated enough to do so. Right now, um, I want to keep this a little bit on the sub 2 hour side, so I don't want to go too much deeper. Let's see if there's anything interesting in raw. Input local match. Raw PCBs. Determining if an incoming packet is covered by a raw PCB, and if so, pass to the user provided receiver callback. Okay. Yeah, so this is just like raw sockets, relatively small compared to, just for fun, since this is a small implementation and smallness is prized, let's take a quick look at the size. What is this called? lwIp? Well, that's not so interesting. So source include. So most of the sizes in apps, which is not so surprising. This is like the higher level stuff. Opt. I don't know what opt is. Prot. Okay, so we've got some protocol headers, including IP, TCP. Should we look at the TCP header? Where are we? Source include. I think we've seen some of this. It's only about 100 lines. And it's things like header length and flags. The massive copyright statement. The header struct, etc. Okay. That's the stuff that I guess is in protocols, which makes sense. Private. Let's look at TCP private. I don't know if we're supposed to be looking in their private area. This is about 500-ish lines. So not a lot. But we've got things like debug printing. I guess that's private because they don't want everyone to dump their TCP packets. We've got a TCP keep alive function. Split unsent sequence. TCP RST, which is reset, right? Reset network interface. And queue flags, send fin. Okay, I don't know why these are, I don't think these are necessarily private for security reasons. I guess they're just internal utility functions. You can purge the PCB and remove it. Free, I guess, some segments. Where's, let's look at TCP ACK. Do, if PCB flags and TCP ACK delay, we're going to clear flags on the PCB, TCP ACK delay, and call ACK now. Otherwise, we're going to set flags ACK delay. Huh. So I guess we don't ACK we don't ACK things right away. We have some delay. Then ACK now is just going to call set flags on ACK now. I guess that's I guess I'll stop there. So what did we learn? We learned a couple of things. One, so the overall structure seems to be that we're on some embedded device and we have some number of network interfaces, and we're going to open up regions of memory. I'm getting the impression that it's mainly like one region of memory because there's one main thread, and that's going to be where things are put. This is this mailbox thing that we saw, or perhaps there's a mailbox per network interface. I don't know, but at any rate, the main loop is going to listen for messages like calls to the API and incoming packets, and it's going to demultiplex or route those messages to the corresponding network interfaces via some system of callbacks. And then the TCP stack part itself seems to be a pretty buttoned up implementation of the TCP standard, and the the logic and the flow of all of that is, if you look at this code with this standard side by side, it should be readily apparent. Whereas I would imagine with something like Linux, there's all sorts of other indirections and optimizations that might be there that might kind of obscure the ability to translate directly from the standards to the implementation. Here, it seems to be like pretty a pretty clear match, and there also seems to be support for some stuff that we didn't look at, including other protocols, and then some apps on top of it, like HTTP. But I figured we might as well focus on the TCP stuff, since that's something we can have a little bit of a sense of from having looked at the Linux kernel implementation. So that's all for me. I'll be doing this again next week, and I've got some stuff, some like coding videos that I'm editing together. It may just end up being one video, but it's starting with like 9 hours of content that I'm editing down. So I think it'll take a few days to get up, but hopefully next week, hopefully early next week, optimistically, but perhaps like in the middle or later in the week. So that's all for me. I hope you all have a good weekend.